Hello everyone, welcome back to Labtube. In this video I'm going to do question 9 from section 16.4, which asks to evaluate the line integral, this is the line integral, using the Green's theorem, and the curve is the positively oriented circle x squared plus y squared. To do this question, let me first recall what is Green's theorem. So Green's theorem says that if you have a line integral of a vector field along a curve with these three properties. First, it is closed curve. So it is closed. That's sometimes we show closeness. 2, it is a simple. It means that it's a simple curve. It means that it doesn't intersect itself. It just goes around once and it doesn't intersect. And third property is that it is oriented positively, meaning that if you move along that specific direction, the inside of the region always stays on your left. Okay? So if you have that kind of line integral, other way of writing this is, so first component dx plus second component dy, c over c. That's other way of writing that. This is equal to a double integral over the region inside the curve, and the integrand is dq dx minus dp dy. That double. Okay, that's Green's theorem, and let's see what we have in this case. In this case, my vector field is here, so x, y. You can see always through this that the coefficient of dx is first component of vector field, and coefficient of dy is the second component. In this case, it is negative x to the power 3. Okay, what about the curve? It is the circle given by this equation. That equation says that the center is 0, 0, so it is the origin, and the radius is 2. Okay? So circle is a closed curve. It is simple because it doesn't intersect itself, but we have to orient it positively. Positive orientation of circle is counterclockwise orientation. So the circle oriented counterclockwise is a closed, simple, positively oriented curve. Okay, that's great. Now we have everything and we're ready to go. Integral of y cubed dx minus x cubed dy over c, and I know that c is closed, simple, and positively oriented. This is going to be equal to double integral inside the circle, which is disk, and the integrand is dq is this guy here. Find its derivative with respect to x. So d of this dx minus this with respect partial derivative of p, which is y cubed, with respect to y. No, with respect to y. Okay. So I have this. Now find partial derivative of this. It is negative 3x squared minus 3y squared. Okay? I have double integral. To evaluate double integral over a circular region, it is better to write that region, which is inside this circle, in polar coordinates. So polar coordinates that describes the disk of radius 2 centered at origin is that theta goes from 0 to 2 pi, and r goes from 0 to 2. Okay, so I can make this. Okay, let me do it. So 0 to 2 pi, 0 to 2 minus 3. Okay, this thing here is minus 3x squared plus y squared. I have to write everything in terms of polar coordinate. But x squared plus y squared is r squared minus 3r squared. This is r dr dt. Okay, great. Now I have written everything, and it is an iterated integral. And now I can evaluate that. This is equal to 0 to 2 pi. I have negative 3r to the power 3, so it's negative 3 over 4r to the power 4. Go from 0 to 2. dr is done, d theta. And plug in 2 there, it is negative 12 minus 0, 0 to 2 pi d theta. And this is negative 12 theta, go from 0 to 2 pi. And this is negative 24 pi. Okay, very quick wrap up. My vector field is this. My curve is the circle. Counterclock was over there, and I want to find this line integral. The way I do that, I change it to a double integral using Green's theorem over the disk, the region inside the circle, and then make it to an iterated integral. But this region is circular. The easy way to do that would be go to the polar coordinate. So I did write that in polar coordinate, do inner one, outer one, and that is the value of the integral. Thank you for watching this video.